Hi, welcome to this is my video number 12, the short video this time. Right, I'll talk on the Volterra solution of the non-homogeneous random integral equation. Volterra solution. All right. So for the non-homogeneous random integral equation, as we know, this is ux is equal to fx plus, in this case I don't put lambda, we just have a 0a to b kxt ut dt. Okay, so we consider this non-homogeneous random integral equation, and we suppose that k is real and continuous in the rectangle x db. So k is real and continuous in R, yeah, where R is all x y such that x in AB and t in AB, and f is continuous, yeah, f continuous, and fx is not zero on some interval I, in I, where I is x in AB, and a function. So we have these three situation. We have a function k r xt reciprocal to k xt exists. Then the solution to that equation, the solution to that is unique and continuous, given by, so let's call this 1. So the solution to 1 is given as ux fx minus integrate a to b k r xt ft dt. So this we call it as a Volterra, known as a Volterra solution. Yeah, known as Volterra solution. Volterra solution to our Fredholm non-homogeneous Fredholm integral equation. So let's see example. I just give you one example, and that's it. Example. So we consider the non-homogeneous Fredholm integral equation, yeah, ux fx plus half integrate 0 to 1 e x minus t ut dt. So if you compare with the general case here, so what we have, fx is fx, and then our kxt is half ext, our a is 0, b is 1, and we know that the reciprocal function kr can be written as minus kr xt. This is from the previous video number 11. This can be written as k1 xt plus k2 xt and so on, kn xt and so on. Okay. Now the solution for this type of equation is given as a Volterra solution there. So we need to find what kr is. So how to find kr? So we start with using the iterated kernel. Yeah, using the iterated kernel, which is we have k1 xt. This is k xt, which is k xt is half ex minus t. Alright, and then the n terms or n iterated xt, this is given as integrate a 0 to 1 k x s kn minus 1 s t ds. Yeah, for n equal to 2 and so on, because 1 is already there. Now we need to find k1, k2 and so on. So we already have k1, so we find k2. So for k2 xt, this is integrate 0 to 1 k x xs k1 st ds. Okay, this is equal to 0 to 1. Our k is kxs, which is half x minus s, and then k1 we have half k1 st, so we have s minus t ds. Again, this is quite simple. You can solve this. You can take out half, and then this is I think this is half squared, right? So we have half squared, right? So integrate 0 to 1. So now I can take out anything that free of s, so we have x ex minus t, so then integrate ds. So this gives you half squared ex minus t. All right, then we can find k3. We can find k3 xt is integrate 0 to 1 k xs k2 st ds. Here we have 0 to 1. This is half ex minus s. k2 we obtained just now. This is that's k2. Yep. 1 over 2 squared s minus t ds. Okay. Then here we can take out all those free from s, so we have 1 over 2 3 ex minus t, integrate 0 to 1, s cancel out, so we have ds. That gives you 1 over 3 cube ex minus t. So now from k1, k2, k3, from k1 we have half to the power 1. This is just the same. And then for k2 we have half to the power 2. For the k3 we have half to the power 3. So therefore we can find what kn is. Yeah, kn is given as 1 over 2, sorry, this is 1 over 2 n ex minus t. So therefore we can have Kn Kr, so negative Kr xt, this is given as K1 xt plus K2 xt plus up to Kn xt and so on. So this is just substitute there. We have K1 is half E x minus t plus K2 is half squared E x minus t and so on. Up to n we have 1 over 2 n E x minus t and so on. Okay, of course you can factor out those. So what we have is half E x minus t. Okay, so we have 1 plus half squared and so on, plus 1 over n minus 1 and so on. So for this part here, this is the geometric series, the summation of those. We have this is a, your 1 over 1 minus your r is half, that give you, this is half, 1 over half, this is 2. So altogether you have this 2 and half cancel out, so we have e to the x minus t. So that's your kr. So therefore kr xt is given as negative e x minus t. So therefore the solution, the volterra solution, is can be written as that. Okay, so using this, so we have let me give a number. So let me give a number. Let's call this there's 1. Let's call this is 2. Okay, so the solution is given, the solution is a volterra solution to 1 is given by 2, which can be written as, you just substitute everything into 2. So we have ux is equal to, we have fx plus, we have negative integrate 0 to 1 kr xt ft dt. Alright, so you can substitute those things, that give you fx minus integrate, so minus you got plus 0 to 1 kr, this is r, kr, it is e x minus t, we have ft dt. If you are given specifically what f is, then of course you can solve those integral. So this is the solution to the given question. Alright, then as an exercise, you can try this. Given ux as x plus integrate 0 to 1 ut dt, you can find the answer is given as, ux is equal to x. So you can try this as an exercise. So as I mentioned earlier that this video is rather short, so I just give one example, which is basically continuation of last video, that's on the volterra solution. Alright, and then I give you one example of how to solve or how to obtain the Volterra solution given the non-homogeneous Fedem integral equation of the second kind. So with that, thank you. We stop here for this video. Bye bye.